hyperclass forcing in Morse Kelley class theory.
Okay, thank you very much for the introduction. I'm really glad to be here and to present my talk. I'm going to talk about hyperclass forcing in Morse Kelley class theory. This is joint work with David Friedman. So let's jump right into it. If you look at forcing notions according to their sizes, so you can get a kind of hierarchy. So you have set forcing that we all know. The forcing theorem holds, the axioms are preserved. Set forcing is very nice. And if you do class forcing instead of C, actually what you do is definable class forcing in general version in a model MA, where M is a model of set of C and A is a predicate. And here the definability lemma holds for pre-tame forcing. So I have to restrict my forcing notion. Sorry, I have to. The axioms are preserved for tame forcing. So also for the preservation of the axioms, you have to introduce a kind of restriction to the forcings that you're looking at. But if you go to the context of MK, for example, Morse Kelley, and you look at class forcing there, then you get that the forcing theorem holds without any restrictions. But for the preservation of the axioms, you need tame forcing again. So what I'm going to do, I'm going to define definable hyperclass forcing in Morse Kelley. So this is kind of as the step. It's similar to the step you're doing when you go from set forcing to definable class forcing in set of C. You're just going from class forcing in MK to definable hyperclass forcing in MK. So hyperclass forcing is a forcing where the conditions are classes. Okay, have a quick look at Morse Kelley class theory that we're using. We have two types of objects, sets and classes. And the axiomatization, you have set axioms. These are just a set of C, like the set of C axioms. Then you have class axioms, foundation, extensionality, replacement. Class comprehension is important. In Morse Kelley, you can quantify over both sets and classes for the formula P. If you look at other class theories like Gödel-Benes, then you have only quantification over sets. And what we also assume is that global choice holds, so we have a well-ordering of the universe of sets. So that's the axiomatization that we're working with. And the models that we're looking at is, they consist of a set of C part M and a family of classes. So every A in this class is a subclass of M, and we use the standard epsilon relation. In this talk, I'm not going to talk about arbitrary models of MK, but beta models of MK. This has technical reasons that will probably not come up later because I don't have time to go into the details, but a beta model is a model where a class is well-founded in M if and only if it's really well-founded. So it's true that the class is well-founded.
You mean a class relation? Or?
Yes. Okay, so just to give you an outline of what I'm doing here, I'm going to define this definable hyperclass forcing, but actually I'm not. So the thing is that I'm going to do something indirectly. So one thing that you should know is if you have a model, and when I say model, I normally mean beta model in this context. It could be that I skip it. So I'm looking at a beta model of MK here. And it's very nice because I can always find, to every such model of MK, I can always find a model of something called, which we call ZMK, which is something like set of C minus power set plus some stuff. And this has strongly inaccessible cardinal kappa. And the main point here is that more or less the sets from the MK model are thought to be in the lower part of this set MK model, and the classes are going to be here. So the height I usually note with kappa star. The idea here is, if you look at the model of MK that you all know, it's something like that, yeah? So kappa is strongly inaccessible. This is a model of MK. And this is kind of a generalized version of this thought. So what we're going to use is that for every MK model that we're looking at, we can find such and such MK model, and vice versa. So actually, instead of talking about hyperclass forcing in this MK model, we will be going to talk about definable class forcing in the set MK model. So this is the kind of setup that we have for this definition. Okay, very good. So let's have a look at this set version of MK models. So actually what we're going to talk about is set MK star. This is a set of C minus, including set bounding. there is a strongly inaccessible cardinal kappa, and every set can be mapped injectively into kappa. So this is the model. It's the star is because we include set bounding explicitly. The reason is just that in set of C minus, bounding does not follow from replacement. So what we're going to do, we're adding this set bounding to the ZMK version, and we're also going to add class bounding. So this is just the class version of the bounding to the MK, and we get MK star. So actually we're working in this MK star. It's always added the bounding axiom. Okay, so just to point out what we're doing again so that you can follow this. We are now going to work in MK star. And if we have a model here and we want to do something like a definable hyperclass forcing over this, to get an extension M of some G, what we're actually going to do is we're going to the context of ZMK star and find a model here, which we call M plus, do a definable class forcing here, because you know what the hyperclass was in the MK star context is now the class in the ZMK context. Get an extension of this, and then go back to the MK star context. So of course what we need for this is that we have kind of a nice correspondence between the MK star and the ZMK star models that we're looking at. And this is actually, we've proven that we can do it in a very nice way. So unfortunately, I can't give you any details on this because I don't have time, but this is the theorem that we're looking at. So what we're doing is we say, starting from a beta model of MK star, we can define a model M plus. So this is defined by some coding such that M plus is unique, it's a transitive set, and it has the properties that it's a model of this ZMK star, which I was talking about. And the classes are just the power set of M in intersection with M plus. And the sets M are V kappa M plus. So this is what I've shown you here. So the idea is that the classes kind of go into the upper part and the sets go into the lower part of the model. And conversely, if we start from a ZMK model that is in that way that we want to have it, then we know that if we define C to be the power set of M in intersection with N, and M to be V kappa of N, then the model that we're getting out of is a beta model of MK star, and the model M plus derived from M equals N. So we have a really nice correspondence between these two types of models here. Okay, so what do we do now if we look at forcing? The first definition actually takes place in MK star, and then we're going to switch. So let's just define the forcing notion and the generic set. Let M be a model of MK star, and then we have a P, which should be an M-definable partial ordering with the greatest element 1. Then you just have the normal definitions that you have. So P, Q, and P are compatible if you have an R which extends P and Q. A definable hyperclass D extends if for all P there is a Q such that Q extends P and Q is an element of D. And G is called a P-generic hyperclass over M if G is pairwise compatible upwards closed subcollection of P and meets every dense subcollection of P, which is definable over M. So this is just the normal definition of generic enforcing in this context. And now what we are going to do to define the extension, because we haven't until now, we are going to the ZMK context. So in ZMK star, the hyperclass that we're looking at, the forcing notion, becomes a subclass of the power set of M in intersection with M plus. The generic that we're looking at is a pairwise compatible upwards closed subclass of P, which meets every dense subclass of P, and which is definable over M plus. So we have in this ZMK star model a nice setup for a definable class forcing that we can work with. We can define names and their interpretation and the extension of M plus as usual in this context. And then we can define the extension, the hyperclass generic extension, in this way that we say we start from the MK star model, we have a definable hyperclass forcing P, and then we go to the M plus model, so we go to the ZMK star context. We do the definable hyperclass forcing there, we get an extension M plus of G, and then from this extension we can go back to the MK star model. So M of G is just the model of MK star derived from this M plus of G And now we have that the sets are the elements of B kappa and plus of G, and the classes are the subsets of B kappa and plus of G and M plus of G. Kappa is the largest cardinal of M plus of G and is strongly inaccessible. And such a model we will call the definable hyperclass generic outer model of M. So it's just what I wrote down here. So we go down, we go to the extension, and then go up again. So this is the setup for the hyperclass forcing. Now, a problem is that I was always talking about definable class forcing in the set MK, but actually we only know definable class forcing in set FC. And set MK is not full set FC, it's set FC minus. So we have to look at some problems that come up in this context. Actually, there are mostly these two problems, because we don't have power set axioms. So we have to ask ourselves, is the forcing notion, even if it's pre-tame, does it follow that it is definable, that the definability lemma holds? So that is something that follows in set FC. In set FC, if your forcing notion is pre-tame, then you get that the definability lemma holds. And even if the forcing notion is pre-tame and the definability lemma holds, does it preserve the axioms of set MK star? So actually one thing that we can prove is that if we have a model of set MK star and P is a pre-tame definable class forcing over M plus, it preserves the inaccessibility of kappa, and the forcing relation is definable, so the definability lemma holds, then the extension is a model of set MK star. But we assume for that the definability lemma holds. So, and we don't really know that if the forcing is pre-tame, then it follows that the definability lemma holds. So we had a little bit of a problem with that. And what we did to solve that, we changed the model that we're looking at. So one of the problems here is that I can't work with the V hierarchy like in normal full set of C. And we kind of circumvented this problem by changing our model in a way that we have another nice hierarchy, the L hierarchy. So what we did is we showed that if we start from such an set MK, yeah, just ignore the second star for a moment. I'm going to say something about it later. So we start from such a model M plus. We have a largest cardinal kappa. Kappa star should denote the height of the model. Then we can find a specific forcing, an M plus definable forcing, such that the definability lemma holds for this specific forcing. P is pre-tame, and this forcing at predicate A in such a way that the model M plus is actually L kappa star of A, and M plus in A is a model of set MK double star relativized to A. So when we can do this, this actually makes it much easier for us to handle the problems that we had with regard to the definability lemma, because now we can use the L hierarchy, and then we can just use the normal proofs that we have in the definable class forcing context that we couldn't do before.
If your original model was already of this form, then you don't need this.
Yes, yes, but we just wanted to look at the kind of generalized case. So the forcing that we're using here is the forcing that I've written down. It's just the conditions are the functions from beta to 2. And what we are adding is this generic predicate A. So this forcing doesn't add any new sets, it just adds the subclass A. And every set of ordinals from M plus is copied into an interval of the generic. And so we have that every set of ordinals is coded by this generic predicate A. And it holds that as P is less or equal kappa closed, it's less or equal kappa distributive. And from this follows that it's pre-tame. And we can show that the definability lemma holds for P. So again, I can't give you details, but this is very nice, or it would be very nice if it would work like that. So we have a small problem here, which lies actually in this very innocent looking thing that if P is less or equal kappa closed, it's less or equal kappa distributive.
I was just going to ask that.
Yeah.
You need definability for that, right?
Yes, yeah, you need more than, I mean, if I would only work in set MK star, it wouldn't work. So we actually need to add another axiom for that to work. So that's the way that we did it. We added this dependent choice axiom to set MK star, and this is only for this small fact that it holds that from the closedness the distributivity follows. So what we are doing, we are adding this dependent choice axiom here to set MK star, and we also have to add the class version to MK star. So we're actually working in this MK double star, set MK double star setting. And we can also prove that the coding that we have between models works for this. So it works just like the MK star set MK star case. Okay, so a last step that we wanted to do is to make A definable, because now, I mean, we changed the set MK star or double star model that we were looking at to this L kappa star of A. And at some point, we want to go back up to the MK case, and then we don't want to have this undefinable predicate that we were working with. So we thought that we want to make this predicate definable. And we proved this theorem here that if I have this model of ZMK double star, which is in this nice way that I described, so I have largest cardinal kappa, kappa star is the height of this model, and from this forcing that we did before, we have that M plus is L kappa star of A, then we can just force that there is an X, which is a subset of kappa, such that L kappa star of A can be extended to L kappa star of X, and ZMK double star is preserved and kappa remains strongly inaccessible. So this is a forcing where we just use almost disjoint forcing for the coding. And before we do that, we actually have to reshape the predicate in a certain way so that we can always find this almost disjoint family that we're working with. So this is just the setup for this. Okay, so now we are actually in a case where we can do what we wanted to do initially, namely do a definable class forcing. So just what we did more or less was this. We went from an MK, in this case it should be double star model to M plus. Then we changed M plus to this L kappa star of A. We extended L kappa star of A to this L kappa star of X. And now actually we're in a setting where we can say, now do the definable class forcing that you would like to do. So something. From this something you get an extension, and from this extension you can go back to the MK star case. So this is the general setup for the hyperclass forcing that we're doing. And I just want to give you an example on how this could work. We looked at minimal models. So a minimal model of ZMK double star should be the least transitive model of ZMK double star containing a real S, and the same for the MK double star. So a minimal beta model MS of MK double star is the least beta model of MK double star containing a real S. And what we showed using this template for hyperclass forcing is that every beta model of MK double star can be extended to a minimal beta model of MK double star with the same ordinals. So the proof very shortly is going to work like the following. We start from this beta model of MK double star, we go to the ZMK double star context. And then in 3 steps, this is 3 extensions, we are going to kind of show that there are no other models, so that the model that comes out is really minimal. So in the first step, we're going to show that there are no ZMK double star models containing X of height between kappa and kappa star. Then we are going to show that there are no cardinals below kappa, so that which are largest cardinals for a ZMK double star model. And in the third step, we're going to show that this holds actually for all ordinals. So there is no ZMK double star model of height less than kappa star containing a real S in which alpha is strongly inaccessible. Then from this, we get a minimal model of ZMK double star. And from this minimal model of ZMK double star, we can go back to the MK double star context. So step 1 is actually just a variant of the forcing that we did when we showed that A is definable. We are just going to change the reshaping forcing a little bit that we used, so that we actually destroy replacement level by level relative to the X. So this is, again, a reshaping and almost disjoint forcing that we do in this step here. In the second step, what we want to do, we want to extend the model that came out of the almost disjoint forcing, this L kappa star of X, to a model such that no cardinal below kappa star can serve as a source for a ZMK double star model, which means, that it is the largest cardinal of a ZMK double star model containing this Y intersection with the cardinal. So this forcing consists of 2 steps that we're doing. The first is we're shooting a clap through a fat stationary set. That's just forcing by Abraham and Schellach that we're using. And in the second step, we want to force all limit cardinals to belong to this clap, and this is an Easton product of collapses. So with these 2 forcings, we get our step 2, and in step 3, what we're showing is that now this model, which came out of step 2, we can extend this to be of a form L kappa star for a real S, such that this is a model of ZMK double star. And whenever we have an ordinal alpha bar, which is less than kappa star, then there is no model of ZMK double star containing S, in which alpha star bar is strongly inaccessible. So actually, we have a minimal model. And this is again in 2 steps. The first is that we add a real R by Jensen coding, and then we use a result by Cy-Friedman on admissibility spectra to extend this model in a way that we want to have it. I'm sorry, I actually have prepared some slides which go into more detail, but I think I have to stop now.
5 minutes.
Okay, good. So I will show you afterwards. I will just going to finish my talk and then I can show you the slide. Okay, so and if we have that, we then can go back to MK double star. This is really easy. We have this L kappa star of S, and from this we can get this model of MK double star that we want to have. So we just take L kappa star of S, L kappa of S, together with a C, where C consists of the subsets of L kappa star in L kappa star of S. Did I say star Tom? Okay. And this, we can show that this is a beta model of MK double star, and it's the least such model containing S. Okay, so actually there are a lot of open questions. I just picked out 3 that I find interesting. The first is, what happens if we drop the beta model assumption that I was always talking about? So everything I did was in beta models. I think the main point here is the coding between the MK double star and ZMK double star, because this is where we really heavily use this beta model assumption, but it should be, we should be able to do it otherwise too. It's just, I guess, more complicated kind of technically. Another point is that actually we were working with 3 different kinds of axiomatization. So we started with MK, we extended this to MK star with the bounding axiom, and then to MK double star with the dependent choice axiom. And now the model, if we, the question is, if we just assume the consistency of MK, are there models of MK that don't satisfy MK star, and models of MK star that don't satisfy MK double star? There's work done by Victoria Gitman and Joel Hampkins, and also Cy-Friedman is doing something on this. And the last thing is, it would be interesting to look at the relationship between MK and second order arithmetic and kind of results that you can take from one to the other. So for example, the minimum model result that we have here, if we do that in second order arithmetic, it becomes much easier, because we then start from a model in second order arithmetic, go to a set of C minus model, and then the kappa that we were looking at is just aleph 0. So a lot of the complicated stuff of the proof kind of just falls out, and we get a nice and easy result. Okay, so this is the first thank you.
Yeah, thank you. So you said you want
I
to lead the discussion, or what is?
I don't know. I mean, I have to stop in kind of 3 minutes or something like that. So.
Yeah.
I will just take questions, and if somebody is asking this question, I can just pull out the slide.
So we have to ask the right question. So who knows a good one? Yeah.
Just a quick one about exactly the structure of stuff you can define using this. So when you move from set forcing to class forcing, something that's really nice, say if you do it over L, is that you get class generic, class generic reals that are not set generic.
Mm-hmm.
You can't get them from set forcing. So, I mean, I think we've talked about this, but a similar phenomenon occurs here. You get hyperclass.
Yeah.
Generic. I mean, how kind of different is that from when you go from set forcing to class forcing, or is it?
It's not very different, because actually, what you're doing is the definable class forcing, so it's more or less straightforward, the same.
I just want to clarify something, because I found it so surprising. I thought it was different. So if you have a model of Z of C minus, and you have a pre-paying class forcing, you don't necessarily get the definability.
Yes, I mean, it could be that there is a proof. We actually weren't able to do that, so we kind of circumvented this problem.
I just assumed that this was the case recently, something I was trying to argue.
Okay. Yeah, I mean, it would be nice if you could find something like that, because then we would have we wouldn't have this problem. It's just because when you look at the normal proofs of this definability lemma context, then you always use, in some sense, the V hierarchy, and we just had the problem that we couldn't make this work in the set of C minus case.
Can you do these things in weaker subsystems of MK, models of finite comprehension?
I'm not quite sure, to be honest. I haven't thought about this until now. We were just, I mean, we were really much focused on doing the opposite, kind of adding accents.
But she's not even doing it in MK itself.
Yeah. But it would be very interesting to see that. I'm sorry, I really haven't thought about this.
Finite comprehension augmented.
Yeah.
In a KP model.
Yes, yeah, that would be interesting to see.
Well, I hope I'm able to phrase the question coherently. If I understood it, so you're starting with this hyperclass forcing, and then you muck the model around a bit to turn it into a regular class forcing. So you force over there, and that's supposed to sort of substitute or represent your original hyperclass forcing.
Yes. Okay.
How do you know that when you change the model by doing these intermediate forcings, that you don't along the way change what's definable?
Yes.
How do you know that your original definition, or there's some substitute definition, that you don't lose information along the way so you can still capture the original forcing?
I think the way that we kind of not handle this problem is by just talking about, I mean, very specifically defining the extension not by this thing here, but just saying that the extension that comes out here is just defined in this way, and we're going to say that this is the actual hyperclass forcing that we wanted to do. So, I mean, you're right, the way that I talked about this, and it's actually the way that I think about this, is to say I have a hyperclass, a definable hyperclass forcing in mind, and I'm going to, instead of doing this, I'm going to do that. But if you look at it like we did it formally we never kind of talked about the hyperclass forcing in a certain sense. We just did this, and I think this kind of circumvents the problem a little bit.
Are the forcings you do gentle enough that you can just kind of tell that you're not really messing up your original forcing definition? Forcing notion?
Yeah, I mean, in a certain sense, we didn't even kind of consider this problem, because what we actually did is to say we don't define this extension by the hyperclass forcing that we have here, but we just define it in this way. So we never kind of had to check if this coincided in a certain sense.
But are you talking about the definability of the forcing, or the definability of the metaclass and the conditions in the forcing?
Well, whatever. I mean, how do you know?
Because the power set of kappa of m plus is just the same as the classes of n, right?
Yeah.
So,
Joshi does this extra forcing to get the model that you want into this elevation? That's the question.
I'm sorry, I didn't get this.
You do this extra forcing to get it into this elevation, right?
Yeah.
But that just means, I guess, whenever you do that class forcing of yours, you always assume you do those forcings first.
Yeah.
Which
Yes,
doesn't
yes, exactly.
harm anything.
Exactly. That's the
essentially
point.
what's
but,
going on.
I mean, should we think of that as a way of kind of preparing the model?
Yes.
So that you can now do the kind of
Yes, exactly.
Hyperclass forcing that you wanted to
Yes.
do in the first place.
Yes, exactly. It's kind of preparatory forcing that we're doing.
Okay. So this leaves the middle of what other slides, but thank you very much.
Probably the right question is, can we